What if I told you that the very fabric of reality, the space between the stars, the air in your lungs, even the atoms that make up your body, isn't as smooth or predictable as it seems? Beneath everything we know, hidden in the tiniest scales imaginable, there's a chaotic, seething ocean of energy and uncertainty. Scientists call it quantum foam, and it's one of the most mind-bending mysteries in the universe. Imagine spacetime itself bubbling like a pot of boiling water, with particles and forces flickering in and out of existence in a frenzy so small, we'll likely never see it directly. This isn't science fiction, it's the frontier of our understanding, where the rules of physics as we know them begin to break down. Now, picture this. Every theory we've ever had about how the universe works, gravity, light, even time, starts to unravel when we zoom in close enough. Quantum foam isn't just some abstract idea, it's the wild, untamed foundation of everything. Think of it like the static on an old TV screen, but instead of random noise, it's the very code of reality glitching in and out. Some physicists believe these fleeting bubbles of energy could be wormholes, shortcuts through space and time. Others think they might hold the key to dark matter, parallel universes, or even the origins of existence itself. The craziest part, we're just starting to scratch the surface, so buckle up because today we're diving headfirst into 30 of the most incredible, outrageous, and awe-inspiring theories about quantum foam. From time-traveling particles to hidden dimensions curled up smaller than an atom, each idea is more bizarre than the last. Some might sound like pure fantasy, until you remember that the universe has a way of being stranger than anything we could invent. By the end of this journey, you might never look at the empty space around you the same way again. Because here's the truth, what looks like nothing might just be the most important something we've ever tried to understand. Ready to explore? Let's go. At the smallest scales imaginable, far, far smaller than an atom, the universe doesn't behave like the smooth, predictable stage we're used to. Instead, it's a churning, turbulent sea of potentiality where space and time themselves lose their meaning. This is quantum foam, and it's not just a quirk of physics, it might be the very scaffolding of reality. Imagine building a house not on solid ground, but on a foundation that constantly flickers in and out of existence. That's what the universe is doing right beneath our feet at every moment. The idea traces back to physicist John Wheeler, who first suggested that spacetime isn't smooth but foamy, like the froth on a wave. At the Planck scale, a distance so tiny it's a million billion times smaller than a proton, particles and energy don't just sit still. They pop into existence, collide, vanish, and reappear in a frenzy so fast we can't directly observe it. But here's the wild part, these fluctuations aren't just noise. They might be stitching the cosmos together like invisible threads holding a tapestry. Without this chaotic dance, space and time as we know them might not even exist. Think of it like pixels on a screen. Zoom in close enough and the smooth image breaks apart into tiny dots, except in quantum foam. The dots are constantly shifting, rewriting the picture of reality itself. Some theories even suggest that these fleeting bubbles of energy could be the seeds of gravity, the glue that binds the universe. If that's true, then everything from the orbit of planets to the pull you feel when you jump is just the echo of spacetime's deepest, most turbulent layer. But here's where it gets even stranger. If quantum foam is the fabric of reality, then our entire universe might be floating on something far more unstable than we ever imagined. It's like walking on a frozen lake, unaware of the swirling currents beneath the ice. One wrong step or one fluctuation too many, and who knows what might happen. Could these tiny ripples open doorways to other dimensions? Could they explain why gravity is so weak compared to other forces? Or could they rewrite the laws of physics entirely? The answers might be hiding in the foam, just waiting to be discovered. Could those tiny bubbles in the quantum foam actually be doorways? Some physicists think so hidden within that frenzied sea of space-time might be microscopic wormholes, little tunnels threading through reality itself. Not the massive, stable portals we see in sci-fi, but fleeting, unstable passages so small they'd vanish before you could even blink. Yet their existence could solve some of the universe's biggest mysteries. Take quantum entanglement, where particles instantaneously influence each other across vast distances, a phenomenon Einstein famously called spooky action at a distance. What if that connection isn't spooky at all, but literal? Imagine two particles linked by one of these wormholes, like secret passageways knitted into the foam. Even if they're light years apart, they'd never really be separated because the wormhole would tether them through a shortcut in spacetime. Suddenly, entanglement isn't magic, it's architecture. And here's where it gets wilder. If these wormholes exist, they might not just connect points in our universe. Some theories suggest they could bridge entirely different dimensions, like roots tunneling through the soil of reality. Picture our cosmos as just one leaf on an infinite tree, with wormholes as the veins linking other hidden leaves. What looks like random quantum foam from our perspective might actually be a bustling intersection of realities, flickering in and out of reach. But don't pack your bags for interdimensional travel just yet. These wormholes would likely collapse faster than they form, crushed by the same violent fluctuations that create them. Yet even their fleeting existence could rewrite physics. Maybe dark matter is just ordinary matter slipping through these microscopic gates, leaking into our universe from somewhere else. Maybe black holes aren't in points, but hubs where wormholes tangle into knots so dense, even light can't escape. The real kicker, we might never see them directly. But like footprints in sand, their effects could be everywhere, woven into the fabric of gravity, etched into the behavior of particles. If quantum foam is reality's blueprint, then wormholes might be its hidden staircases. And who knows, one day we might just learn to climb them. What if time itself wasn't as uniform as we think? Down in the quantum foam, where space-time churns like a stormy sea, there might be microscopic pockets where time doesn't just flow, it stutters, speeds up, or even loops back on itself. These could be time dilation bubbles, fleeting glitches in reality so small you'd never notice them, but with consequences that rewrite our understanding of the universe. Picture a calm pond, its surface smooth and steady until a fish jumps, creating ripples that distort the reflection. Now imagine those ripples aren't just bending light, but time itself. In quantum foam, the violent fluctuations of energy could twist spacetime into tiny knots where time behaves unpredictably. One bubble might tick slower than the surrounding universe, like a watch submerged in molasses. Another might flicker forward, a fraction of a second ahead of everything else. These wouldn't be the grandiose time machines of sci-fi, but something far stranger, natural, chaotic distortions baked into the fabric of reality. Here's where it gets even more mind-bending. Quantum mechanics already shows us that particles can exist in multiple states at once until observed when they choose a single reality. What if that uncertainty isn't just about position or momentum, but time? A particle might briefly exist in a time bubble where the future and past overlap, explaining why quantum behavior seems to defy classical physics. It's as if the universe itself is constantly editing its own timeline on the smallest scales, leaving behind clues in the form of quantum weirdness. Some theorists take this further, suggesting these bubbles could be the key to understanding black holes or even the Big Bang. Near a black hole's singularity, where gravity warps time to extremes, quantum foam might be churning out countless micro-time warps, stretching and compressing reality like taffy. And if time bubbles existed in the early universe, they could explain why some regions expanded faster than others, seeding the vast cosmic structures we see today. The wildest possibility, these bubbles might not stay microscopic. Under extreme conditions like near a collapsing star or in a particle accelerator, they could briefly grow large enough to affect matter. Imagine a lab experiment where particles suddenly vanish, only to reappear moments later with no memory of the gap. Could they have slipped through a time bubble, experiencing a few seconds out of sync with our world? It sounds like fantasy, but the math doesn't rule it out. Of course, we're skating on the edge of speculation here. Time dilation bubbles are a tantalizing, what-if, not proven fact. But that's the beauty of quantum foam. It's a frontier where the rules are still being written. Every flicker of energy, every twist of spacetime might be hiding a secret, waiting to reshape our understanding of time itself. And if we ever learn to tap into these bubbles, well, the word impossible might just lose its meaning. What if the greatest mystery in modern cosmology, dark energy, has been hiding in plain sight, churning beneath the surface of reality itself? Scientists estimate that roughly 68% of the universe is made of this enigmatic force, pushing galaxies apart faster and faster. But where does it come from? The answer might lie in the quantum foam, where the vacuum of space is anything but empty. Picture this: every cubic centimeter of so-called empty space is actually a seething battlefield, where particles and antiparticles constantly emerge and annihilate in bursts of raw energy. These quantum fluctuations aren't just random noise, they generate a staggering amount of latent power. In fact, if you could harvest all the energy in a single light bulb's worth of space from the quantum foam, you'd have enough to boil every ocean on Earth. Now multiply that by the vastness of the cosmos, and suddenly, we're talking about a force powerful enough to stretch the very fabric of the universe. This idea turns conventional cosmology on its head. Most models treat dark energy as a smooth, uniform field permeating space. Think of it like an invisible mist gently pushing everything apart. But if quantum foam is the source, then dark energy isn't smooth at all. It's a roiling, chaotic sea of microscopic energy spikes, like a stormy ocean where every droplet is a tiny explosion. The catch: on average, these fluctuations could still create the net effect we observe, an accelerating universe. It's like blowing up billions of microscopic balloons inside a box. Individually, they're chaotic, but collectively, they'll push the walls outward. Not everyone's convinced, of course. Some theorists argue that quantum foam's energy should cancel itself out, leaving no net force to drive cosmic expansion. Others suggest that if dark energy came from these fluctuations, its strength would be unimaginably larger than what we measure. But here's where it gets fascinating. Certain quantum gravity models propose that the foam's structure might naturally suppress most of this energy, leaving behind just the faint, pervasive push we call dark energy. It's like a cosmic pressure valve, bleeding off just enough power to shape the universe without tearing it apart. The implications are staggering. If quantum foam fuels dark energy, then the fate of the cosmos, whether it keeps expanding, rips itself to shreds, or collapses back on itself, depends on the behavior of spacetime at scales we can't even see. It's a humbling reminder that the biggest forces in the universe might spring from the smallest, most frenetic corners of reality. And if we're right, then every inch of nothingness around us is quietly, tirelessly rewriting the future of everything. Black holes aren't the cosmic vacuum cleaners we once thought, leaking energy back into the universe in a slow, ghostly whisper. This is Hawking radiation, and its origins might be tied directly to the chaos of quantum foam. Picture a black hole's event horizon, the point of no return where gravity's grip is so strong even light can't escape. Normally, we'd expect nothing to get out, but quantum foam doesn't play by normal rules. Here, particles and antiparticles flicker into existence in pairs, borrowing energy from spacetime itself before vanishing again in a split second. Most of the time, they annihilate each other harmlessly, but right at the edge of a black hole, something bizarre happens. One particle might get sucked past the horizon while its partner escapes, stranded in the universe with nothing to annihilate. That orphan particle carries energy it technically stole from the black hole's gravitational field. Over eons, this slow trickle of escaping particles bleeds the black hole dry, causing it to shrink and eventually evaporate altogether. It's like a tire with an invisible puncture, leaking air so slowly you'd need a telescope to notice. But here's where quantum foam cranks up the strangeness. Those particle pairs aren't just random, they're born from the foam's violent fluctuations, tiny wrinkles in spacetime that act like cosmic midwives for matter and antimatter. The math suggests that without quantum foam's frantic energy, Hawking radiation wouldn't exist. The foam doesn't just enable the process, it drives it like an unseen engine humming beneath reality's surface. Some theorists go further, proposing that the foam's behavior near a black hole's horizon isn't uniform. Instead of a smooth quantum fizz, there could be concentrated hotspots, regions where fluctuations are more intense, creating bursts of radiation that accelerate the black hole's decay. Imagine a block of dry ice sublimating unevenly, with some patches vanishing faster than others. If true, this would mean black holes don't fade quietly. They sputter and cough, their final moments marked by erratic flares of energy. Even wilder, the foam's influence might solve a paradox haunting physicists for decades. If black holes evaporate, what happens to all the information they swallowed? Quantum mechanics says information can't be destroyed, yet black holes seem to erase it. But if the foam's fluctuations encode data in the fleeing radiation, like cosmic Morse code etched into particles, then nothing's truly lost. The foam could be nature's backup drive, preserving the universe's secrets in the most chaotic way possible. Of course, testing this is a nightmare. Hawking radiation is unimaginably faint for all but the tiniest black holes, and we've yet to detect it directly. But if we ever do, its fingerprints might reveal quantum foam's role in the universe's most mysterious balancing act, where destruction and creation, gravity and quantum chaos are locked in a dance older than time itself. What if everything you've ever seen, touched, or experienced, the entire three-dimensional universe, is nothing more than a projection, like a movie playing on the surface of something far stranger? This isn't the plot of a sci-fi film. It's a serious theory called the holographic principle, and it suggests that reality as we know it might be a cosmic illusion, with all the information in our universe encoded on a two-dimensional surface at its boundaries. And the key to this mind-bending idea, quantum foam, think of it like a credit card hologram, those shiny stickers that seem to show a 3D image when you tilt them. The image isn't really inside the sticker, it's a flat surface encoding all the information needed to create the illusion of depth. Now imagine that, but on a universe-sized scale. Every star, every galaxy, even the space between them, could be nothing more than data imprinted on the quantum foam's turbulent boundary, with our 3D reality just a shadow it casts. It's a concept that traces back to the work of physicists like Leonard Susskind and Gerard T. Hooft, who argued that black holes might hold the ultimate clue. The information swallowed by a black hole isn't lost inside it but smeared across its event horizon like ink on a balloon. Stretch that idea to the cosmos and suddenly the universe starts to look like the ultimate hologram. String theory takes this even further. If the universe's fundamental building blocks are tiny, vibrating strings, then the quantum foam could be the screen those strings project onto. A flickering, chaotic canvas where the vibrations of strings translate into the particles, forces, and even the dimensions we experience. In this view, the foam isn't just the foundation of reality, it's the hard drive storing the universe's operating system. But how could something as flat as a boundary encode something as rich as our 3D world? Picture a computer simulation. Every detail in a video game, the textures, the physics, the lighting, is ultimately just code, ones and zeros on a chip. The holographic principle suggests nature does the same thing, with the quantum foam's fluctuations acting like pixels on a cosmic display. Even time and space might not be fundamental, just emergent properties of this deeper, more abstract information layer. The implications are staggering. If true, it means the universe has a maximum resolution, a smallest possible unit of meaning, just like a hologram can't store infinite detail. It also hints that our perception of free will, of movement, even of separateness, might be illusions woven by the way this data is rendered. Two particles on opposite sides of the galaxy could be linked not because of spooky action at a distance, but because they're projections of the same underlying code. Not everyone's convinced, of course. Critics argue that without direct evidence, the holographic principle remains a beautiful metaphor rather than proven physics. But supporters counter that it solves some of cosmology's biggest puzzles, like how to reconcile gravity with quantum mechanics. If gravity isn't a force in 3D space but a ripple in the 2D data layer, suddenly the math starts to align. Whether or not the holographic principle holds up, it forces us to ask a profound question: what is real? If quantum foam is the universe's hard drive, then reality might be the grandest illusion of all, a show staged on the surface of something infinitely stranger, playing out in dimensions we're only beginning to imagine. And if that's the case, then the answers to life's biggest mysteries might not be out in the stars, but written in the foam's hidden, flickering script. One of quantum mechanics' greatest mysteries isn't about what particles do, but why they ever stop doing it. Take Schrödinger's famous cat, simultaneously alive and dead until someone opens the box. In the quantum world, particles exist in multiple states at once, a blur of possibilities called superposition. Yet when we measure them, they snap into one definite reality. Why? The answer might be hiding in the quantum foam, where spacetime's chaotic churn could be nature's ultimate decider. Imagine tossing a handful of confetti into a hurricane. No matter how carefully you arrange the pieces, the storm will scatter them beyond recognition. That's what quantum foam might do to delicate superpositions. Every fluctuation, every particle-antiparticle pair bubbling up from the void kicks quantum systems like microscopic pebbles, disrupting their fragile coexistence of states. Over time, these relentless nudges add up, forcing particles to choose a single state. It's as if the universe itself is impatient with uncertainty, erasing quantum weirdness through sheer background noise. This idea, called environmental decoherence, isn't entirely new. Scientists have long known that interactions with the outside environment, a stray photon, a passing atom, can collapse superpositions. But quantum foam offers something radical, an environment that's always there, even in perfect vacuum. No lab is ever truly isolated because space-time itself is never still. The foam's ceaseless activity means there's no hiding from decoherence. It's baked into the fabric of existence. Some theorists take this further, suggesting the foam doesn't just passively disturb quantum states, it selects them. In certain interpretations of quantum mechanics, superpositions collapse when they entangle with a larger system. But what counts as larger? The foam's infinite complexity might act like a cosmic observer, constantly measuring the universe by sheer brute force interaction. Picture 1,000 cameras snapping photos of a shy celebrity from every angle. Eventually, the subject has no choice but to behave. If this is true, it solves the measurement problem without invoking conscious observers or parallel worlds. The foam becomes the ultimate arbiter of reality, its chaos sculpting order from quantum potential. Even crazier, this process might explain why large objects like cats or chairs don't exist in superpositions. Their countless particles are constantly bombarded by foam-induced decoherence, freezing them into the familiar, definite world we see. Not everyone's convinced, of course. Critics argue that decoherence doesn't fully explain why one outcome is chosen over another, just why we see only one. Others suggest quantum gravity effects might stabilize superpositions in unexpected ways. But if the foam really is erasing quantum magic behind the scenes, it means the universe has been quietly editing its own script all along, rewriting possibilities into certainties one fluctuation at a time. And that raises a wild question. Without the foam's noise, would reality ever settle down at all? The Big Bang wasn't just a beginning, it was a revolution, a fraction of a second where the universe expanded faster than light itself. But what set it off? What cosmic switch flipped, sending spacetime into hyperdrive? The answer might be hiding in the quantum foam's primordial chaos. Picture the universe before the bang, not empty, but seething with foam's raw energy, a broth of spacetime fluctuations so violent they could no longer contain themselves. According to some theorists, inflation wasn't just an event. It was a chain reaction, a runaway explosion ignited by the foam's instability. Here's how it could work. In those first incomprehensible moments, the quantum foam wasn't just bubbling, it was boiling over. Every fluctuation strained against the fabric of space-time, like steam building in a pressure cooker. Most of these bubbles popped harmlessly, vanishing as quickly as they formed. But one, or maybe a handful, did something extraordinary. Instead of collapsing, they grew, fed by a feedback loop where each expansion created more space for foam to fluctuate, which in turn drove more expansion. It's like a match dropped in a dry forest. One spark triggers an unstoppable blaze. This idea turns inflation from a smooth cosmic crescendo into something far wilder, a quantum riot where the universe's fate hinged on random fluctuations. The math suggests these runaway bubbles wouldn't just grow, they'd stretch spacetime so violently that regions smaller than a proton could inflate to the size of a galaxy in less than a blink. And here's the kicker, the seeds of everything we see today, galaxies, planets, even the voids between them, might be microscopic wrinkles in those primordial foam bubbles, stretched to cosmic proportions by inflation's relentless pull. But why would foam fluctuations trigger this instead of just fizzling out? Some models propose that the foam's energy wasn't evenly distributed. Certain regions might have been stickier, their fluctuations lasting just a fraction longer, long enough to tip the scales from chaos to creation. Think of it like shaking a soda bottle. Most bubbles rise and burst, but one might catch the rim just right, triggering a geyser. In the quantum foam's case, that geyser became the universe. The implications are staggering. If inflation was foamy, then our cosmos isn't just one expanding bubble. It could be one of countless others in a frothy multiverse, each with its own physics, its own destiny. Some might have collapsed instantly, others could be still inflating, their edges forever beyond our reach. And if the foam's fluctuations were truly random, then the laws governing our universe, the strength of gravity, the mass of electrons, might just be a roll of the dice, one outcome in an infinite sea of possibilities. Critics argue that without direct evidence, this remains speculation, but supporters point to subtle clues like the faint patterns in the cosmic microwave background, the afterglow of the Big Bang. Those ripples might bear the fingerprints of quantum foam's earliest tantrums stretched across the sky. If we're right, then every star, every atom, is the echo of a foam bubble that refused to pop. And that means the universe wasn't just born from chaos, it is chaos frozen in flight, its wild beginnings woven into the very fabric of reality. Every flicker in the quantum foam might be more than just a blip in our universe, it could be an entire cosmos springing to life. Imagine each tiny bubble of spacetime's turbulence not collapsing back into nothingness, but pinching off into its own independent reality, birthing a parallel universe with its own laws, its own history, its own version of you. This isn't just speculation. It's a radical twist on the many worlds interpretation of quantum mechanics, where every decision branches reality into infinite alternatives. But here, the branching isn't just metaphorical, it's physical, etched into the fabric of spacetime itself. Think of the foam like a pot of water on the verge of boiling. Most bubbles rise, burst, and vanish. But what if some don't? What if, instead of popping, they detach completely, becoming self-contained droplets floating away? In this scenario, each droplet is a new universe carrying a slightly, or wildly different configuration of reality. Maybe in one, gravity is stronger, making stars burn out faster. In another, electrons have a different charge, preventing atoms from ever forming. And in some, every choice you didn't make here plays out in infinite variations. The foam isn't just chaotic, it's creative, a ceaseless assembly line of alternate realities. The many worlds interpretation already suggests that quantum events spawn parallel timelines. But in this foam-driven multiverse, those timelines aren't abstract, they're physical, each one a literal bubble of spacetime budding off from the quantum froth. It's the difference between tracing forks in a roadmap and watching new roads materialize under your feet. And if that's true, then the foam isn't just beneath everything, it's beside everything. A hidden lattice of universes we'll never see, but whose existence could explain why quantum particles behave so strangely. Here's where it gets even wilder. If every fluctuation can spawn a universe, then the foam isn't just producing random duplicates. It's generating every possible variation of physical laws, like a cosmic mad scientist running endless experiments. Most might be stillborn universes where gravity is too weak to form galaxies, or where the nuclear forces can't fuse hydrogen. But a rare few, by sheer statistics, would have just the right conditions for life. This is the anthropic principle on steroids. We don't live in a special universe, just a lucky one in an infinite foam of failures. Critics argue this is untestable, a metaphysical shrug rather than science. But supporters counter that the foam's multiverse could leave fingerprints. If two bubble universes brushed against each other in the early cosmos, their collision might have left scars in the cosmic microwave background, ghostly imprints we could one day detect. Others suggest that gravity itself might leak between bubbles, subtly altering its strength in ways we could measure. Whether or not we ever find proof, the idea forces a staggering perspective. The quantum foam might not just underpin our reality, but endlessly replicate it, with every flicker a big bang in miniature. And if that's true, then the most profound question isn't why our universe exists, it's why we ended up in this particular bubble, instead of the infinite others whispering just beyond the edge of spacetime. What if consciousness isn't just a fluke of biology, but something woven into the fabric of reality itself? This is where quantum foam collides with one of science's greatest mysteries, the nature of awareness. At first glance, the idea seems outrageous. How could chaotic spacetime fluctuations have anything to do with the shimmer of thought, the glow of self-awareness? Yet some physicists and philosophers argue that the link might be deeper than we ever imagined, hiding in the foam's restless dance. Take panpsychism, the radical theory that consciousness is a fundamental property of the universe, like mass or charge. In this view, even particles flickering in the quantum foam might possess a whisper of subjective experience, not as rich as human thought, but some primal form of feeling. It's not that electrons are pondering philosophy, but that the raw ingredients of awareness could be baked into reality at the smallest scales. Think of it like pixels on a screen. Individually, they're just dots of light, but together they create a vivid image. Similarly, countless micro-conscious events in the foam might combine to form the full spectrum of minds we recognize. Now, here's where quantum foam throws a wrench into the works. If consciousness is tied to these fluctuations, then every decision, every moment of awareness might be shaped by spacetime's turbulence. Imagine your thoughts as a boat on a stormy quantum sea. Sometimes the waves cancel out, leaving calm, focused mental states. Other times they amplify unpredictably, sparking creativity, intuition, or even dreams. This isn't just poetic metaphor. Some researchers suggest that microtubules in brain cells, tiny structures that might harness quantum effects, could act as antennas, tuning into the foam's vibrations. Skeptics, of course, dismiss this as speculation. Consciousness is messy enough without dragging quantum mechanics into it. But proponents counter that the foam's unpredictability mirrors the very nature of subjective experience. Why do thoughts seem to emerge from nothingness? Why does creativity strike at random? If the mind is truly interacting with the foam's chaos, then free will might not be an illusion, just an intimate dialogue with spacetime's deepest layer. The implications are staggering. If consciousness is rooted in quantum foam, then artificial intelligence might never wake up unless it taps into the same turbulence. Near-death experiences could be moments when the brain's quantum processes sync with the foam's rhythm, glimpsing reality beyond the filter of ordinary perception. Even psychiatric conditions like schizophrenia might reflect an overactive connection to the foam's noise, where the boundary between inner and outer worlds blurs. This isn't just fringe thinking. Nobel laureate Roger Penrose has speculated that quantum processes in the brain could explain consciousness, though he stops short of invoking foam directly. Others, like philosopher David Chalmers, argue that even if the details are wrong, the foam consciousness link forces us to confront the hard problem. Why does any of this feel like something at all? Whether the theory holds up or not, it challenges our deepest assumptions. If quantum foam and consciousness are entwined, then reality isn't just out there, it's in here, shaping and shaped by the very act of observation. And that means the universe might not just be aware of itself through us, it might be aware with us in ways we're only beginning to fathom. Dark matter is the universe's most persistent ghost. It outweighs normal matter 5 to 1, sculpts galaxies with its gravity, yet refuses to interact with light or anything else we can detect. For decades, physicists have chased particles like WIMP or actions to explain it. But what if the answer isn't a particle at all? What if dark matter is something far stranger? Quantum foam frozen into cosmic scale structures. Picture the quantum foam's chaotic churn where spacetime flickers like static. Most of these fluctuations vanish instantly, but under the right conditions they might not dissipate entirely. Instead, they could clump together like foam bubbles merging into a larger mass. These wouldn't be ordinary particles, they'd be knots of warped spacetime itself, invisible because they're not made of matter, but of spacetime's twisted geometry. Imagine a net woven from the fabric of reality, draped across the cosmos, too fine to see, but heavy enough to bend the paths of stars with its gravity. This idea flips traditional dark matter theories on their head. WIMP, weakly interacting massive particles, are hypothetical subatomic particles that barely interact with anything except gravity. Actions are ultra-light particles theorized to drift through the universe like an invisible mist. Both are elegant ideas, but decades of searches have turned up nothing. Quantum foam offers a radical alternative. Dark matter isn't made of things at all, but of spacetime's own crumpled texture. Here's how it could work. In the early universe, as spacetime expanded and cooled, some regions of quantum foam might have frozen mid-fluctuation, locking their chaotic energy into stable configurations. These wouldn't emit or absorb light, they'd be more like gravitational shadows, distortions in the backdrop of reality. Over billions of years, these shadows could have gathered into vast, diffuse halos around galaxies, their combined gravity explaining why stars orbit faster than visible matter alone should allow. It's like gluing extra weight to a spinning record. You can't see them, but you can feel their pull. Critics argue that this clashes with certain cosmic observations. If dark matter were truly spacetime foam, shouldn't its distribution look different than what we measure? Yet proponents counter that foam structures could mimic particle behavior on large scales, clustering just like WIMP while remaining fundamentally different under the hood. The key difference: quantum foam wouldn't require new particles, just a new way to think about spacetime's hidden architecture. Even wilder, this could explain why dark matter seems to avoid normal matter, barely interacting except through gravity. If it's made of spacetime knots, it wouldn't collide with atoms any more than a gust of wind bumps into individual raindrops. They exist on entirely different levels of reality. Of course, proving this is a monumental challenge. Detecting spacetime foam directly might require technology we haven't invented yet, like quantum gravity sensors or ultra-precise cosmic microwave background scans. But if we're right, then dark matter isn't an exotic substance, it's the universe's own scaffolding, left behind when the quantum froth of creation froze into place. And that means the missing mass of the cosmos might have been hiding in plain sight all along, woven into the very fabric of the void. Light has a speed limit, 299,792 kilometers per second, and not a single photon in the universe seems able to break it. But why? What cosmic rule enforces this ultimate traffic law? The answer might not lie in some abstract principle, but in the messy, turbulent reality of quantum foam. Imagine light not as a smooth wave gliding through empty space, but as a surfer battling through choppy waters, forced to slow down by the very texture of spacetime itself. At the smallest scales, quantum foam isn't just empty, it's a storm. Particles and forces flicker in and out of existence, warping spacetime like waves in a turbulent sea. When a photon journeys through this chaos, it doesn't get a free pass. Each fluctuation acts like a tiny speed bump, a microscopic detour that forces the light to zigzag ever so slightly. Over vast distances, these deviations add up, effectively creating a kind of friction that caps how fast light can travel. It's not that photons are lazy, they're just navigating an obstacle course woven into the fabric of reality. This idea flips the script on how we think about light speed. Instead of some fundamental law written in stone, the cosmic speed limit could be an emergent property, a consequence of spacetime's rough terrain. Think of it like driving on a highway riddled with potholes. No matter how powerful your engine, you can't hit top speed without shaking your car apart. For light, quantum foam might be those potholes, not enough to stop it, but enough to enforce a universal maximum. The math behind this is mind-bending. Some models suggest that as photons interact with the foam's fluctuations, they don't just slow down, they stumble, briefly scattering off virtual particles or even tunneling through microscopic wormholes. These detours are unimaginably short, but across billions of light years, they ensure no photon ever outruns the universe's built-in drag. Even stranger. This could explain why light speed is constant in a vacuum. The foam's turbulence is uniform enough that every photon, no matter its energy, faces the same rough road. Critics argue that if foam friction were real, we'd see subtle variations in light speed, especially for ultra-high-energy photons from distant gamma-ray bursts. Yet so far, the speed of light remains unshakably consistent. Supporters counter that the foam's effects might be too fine-grained to detect with current technology, or that they cancel out statistically over large distances. Either way, the idea challenges our assumptions. What if light speed isn't a law but a symptom? A cosmic traffic jam imposed by the universe's own restless foundation. And here's the wildest twist. If quantum foam governs light speed, then altering the foam's structure, say near a black hole or in a lab experiment, might temporarily bend the rules. Imagine stretching spacetime until its foam smooths out, creating a corridor where light briefly speeds up. It sounds impossible, but if the foam is the key, then the universe's ultimate speed limit might not be so absolute after all. Just another mystery hiding in the chaos beneath our feet. Einstein called it spooky action at a distance, the bizarre phenomenon where two entangled particles, no matter how far apart, instantly mirror each other's states. A flip here, an immediate flip there, with no signal traveling between them. It defies common sense, as if the universe cheats by skipping the middleman. But what if the quantum foam holds the secret to this cosmic sleight of hand? Not through magic, but through hidden architecture, tiny, twisting pathways woven into the foam itself, stitching particles together across the void. Picture entangled particles not as separate objects, but as two ends of the same invisible thread. Normally, we'd expect that thread to stretch through space, vulnerable to snapping over distance. But in the quantum foam, space isn't smooth and linear. It's a tangle of fluctuations, a labyrinth where shortcuts might exist. Some theories suggest these particles are linked by microscopic wormholes, threads of distorted spacetime so small they'd make a proton look vast. Every flicker in the foam could momentarily open these passageways, allowing information to bypass conventional space entirely. It's like two cities connected not by a highway, but by a secret subway tunnel running beneath the streets. Here's where it gets even stranger. These wormholes wouldn't be static tunnels, they'd be as dynamic as the foam itself, constantly forming and collapsing in a quantum dance. When one particle changes, the foam between them might reconfigure just enough to transmit that change instantly, like a game of telephone played with spacetime's own static. This wouldn't violate relativity's speed limit because no signal is actually traveling through space. Instead, the foam's hidden geometry allows particles to cheat the system, updating in lockstep because they're fundamentally closer in the foam's tangled web than they appear in our three-dimensional view. Critics argue this sounds suspiciously like sci-fi. After all, wormholes are traditionally the stuff of black holes and warp drives, not subatomic particles. But supporters point to the math. Certain quantum gravity models predict that the foam's structure naturally fosters these microscopic bridges, especially in high-energy environments like the early universe. If true, entanglement isn't a glitch, it's a feature hardwired into reality's blueprint. The implications ripple outward. If entanglement relies on foam-borne wormholes, then every quantum connection might be a tiny echo of spacetime's deepest structure. Dark energy's acceleration, black hole information paradoxes, even the nature of gravity itself could all trace back to these invisible threads. Suddenly, the universe starts to look less like a collection of isolated objects and more like a vast network with the quantum foam as its living, pulsing infrastructure. Of course, proving this is another challenge entirely. Wormholes this small would evaporate almost instantly, leaving no trace for our instruments to catch. But indirect evidence might lurk in the way entangled particles behave under extreme conditions, say, near a black hole's event horizon where spacetime's fabric is stretched to its limits. If their connection strengthens or warps in predictable ways, it could hint at the foam's hidden handiwork. Either way, the idea forces a humbling perspective. What we call spooky might just be spacetime's way of showing its seams. The quantum foam doesn't just fill the gaps between things. It might be the glue holding them together, whispering secrets across the cosmos in a language we're only beginning to decode. And if we're right, then every entangled pair is a reminder that the universe's most intimate conversations happen not in the open, but in the shadows beneath reality's floorboards. The fate of the universe might come down to a cosmic tug-of-war, with quantum foam as the invisible referee. On one side stands heat death, the grim finale where entropy wins, stars burn out, and spacetime stretches into an endless frozen void. On the other, the big crunch, a dramatic rebirth where the universe collapses back on itself, only to explode anew in another big bang. Between these two extremes, the quantum foam's restless energy could be the deciding factor, quietly tilting the scales toward annihilation or resurrection. Start with entropy, the universe's slow slide into disorder. As galaxies drift farther apart and black holes evaporate, you'd expect the quantum foam to calm down, its fluctuations fading like embers in a dying fire. But some models suggest the opposite, that as spacetime stretches thinner, the foam's chaos might amplify, like static growing louder in an empty room. Virtual particles would pop into existence in a vacuum too vast to cancel them out, their energy bleeding into the void. Over trillions of years, this could turn the cosmos into a seething, low-temperature soup, where even the foam's last flickers can't spark new structure. Heat death wouldn't just be cold, it'd be a quiet riot of futile energy, the universe's final gasp. Yet there's another possibility. What if the foam's fluctuations aren't just noise but a self-correcting mechanism? Think of spacetime as a rubber band stretched too far. At some critical point, the foam's latent energy, its relentless pressure against the vacuum, might snap everything back. Instead of fading, quantum bubbles could begin merging, their combined gravity pulling the cosmos inward. Galaxies would reverse course, racing toward each other as space itself puckers like a deflating balloon. The final moments would be apocalyptic, stars colliding, black holes merging, space-time churning into a quantum froth so dense it triggers a new singularity. The big crunch wouldn't be an end, but a reset, a cosmic try-again screen. This debate hinges on a deeper mystery. Is the foam's energy finite or self-renewing? If it's like a battery, eventually drained by expansion, heat death wins. But if it's more like a spring, storing tension until it recoils, the universe might be cyclical. Some string theorists even propose that the foam's microscopic dimensions could harbor hidden energy reservoirs, bubbling up to reverse entropy when least expected. It'd be like finding a hidden gear in a clock, one that starts ticking backward after millennia. Of course, we're speculating across timelines no human will ever witness. But clues might lurk in today's universe. If dark energy's push weakens over time, or if quantum foam leaves faint imprints in the cosmic microwave background, we could glimpse the cosmos's ultimate trajectory. Until then, the question lingers: is the universe a one-act tragedy, or an endless play where the foam pulls the curtain up again and again? The answer, it seems, is written in the chaos we can't even see. What if the quantum foam isn't just the foundation of reality, but its processor? Every flicker, every bubble popping in and out of existence could be more than random noise. It might be the universe computing itself, performing operations on a scale so vast we're just beginning to grasp the implications. This is the heart of digital physics, a radical theory that suggests spacetime itself operates like a cosmic quantum computer with the foam as its circuitry. Think of the universe as an unfathomably complex simulation, but instead of running on silicon chips, it's built on the chaotic churn of quantum foam. Each fluctuation isn't just a blip, it's a logical operation, a binary switch flipping between 1 and 0, existence and oblivion. Over countless iterations, these tiny calculations could add up to everything we see: stars forming, particles interacting, even consciousness emerging. It's like watching a pixelated image resolve on a screen, except the pixels are spacetime itself, and the screen is the entire cosmos. This idea isn't pure speculation. Pioneers like Conrad Zuse and Edward Fredkin argued that the universe might fundamentally be discrete, not continuous, more like a chessboard than a blank canvas. In their view, the foam's fluctuations aren't just quantum quirks, they're bits of information processing the rules of reality in real time. Even gravity and electromagnetism could be emergent properties, the universe's way of rendering the output of these hidden computations. Imagine gravity not as a force, but as a glitch in the cosmic code, a bug that creates the illusion of attraction between masses. The wildest twist: if the foam is computing reality, then the universe might not just contain information, it might be information. Every particle, every law of physics could boil down to data structures in a grand program. Suddenly, the search for a theory of everything isn't about finding deeper forces, but reverse engineering the universe's source code. And just like in a computer, there might be limits to its resolution. The Planck length, the smallest meaningful distance, could be the universe's pixel size, with the foam's fluctuations representing the refresh rate of reality itself. Critics argue this is philosophy disguised as physics. Without direct evidence, how could we ever prove the cosmos is computational? But supporters point to eerie parallels. Quantum entanglement mirrors error correction in distributed computing. The holographic principle suggests information isn't stored in volumes but on surfaces, just like a computer's memory. Even entropy, the universe's arrow of time, could be the inevitable heat generated by cosmic processing. If the foam truly is a quantum computer, it raises staggering questions. Who or what wrote the program? Are we just subroutines in a simulation, or is the universe self-programming, evolving its own algorithms through trial and error? And if reality is code, could we one day hack it? The answers might be hiding in the foam's ceaseless calculations, waiting for us to debug the deepest layers of existence. Gravity feels so fundamental, the force that keeps your feet on the ground and planets in their orbits. But what if it's not a force at all? What if gravity is just an illusion, a side effect of something far deeper happening in the quantum foam's chaotic depths? This wild idea suggests that gravity might not be fundamental like electromagnetism or the nuclear forces, but something that emerges from the collective churn of spacetime's smallest fluctuations. Imagine walking into a crowded stadium where thousands of tiny movements, people shifting, standing, waving, create the illusion of a single, sweeping wave rolling through the stands. Gravity, in this view, is that wave, and the quantum foam is the crowd. The concept flips Newton and Einstein on their heads. For centuries, we've treated gravity as a basic building block of reality, whether as a pull between masses or a bend in spacetime. But at the Planck scale, where quantum foam reigns, these smooth descriptions break down. Here, spacetime isn't curved, it's fractured, a seething mess of virtual particles and fleeting wormholes. Some theorists argue that gravity's gentle tug might just be the net effect of all this chaos, like the average hum of a roaring marketplace. Zoom in close enough, and there's no gravity. Just a trillion tiny spacetime wrinkles pushing and pulling in a way that, from a distance, looks like a unified force. String theory offers a tantalizing clue. In certain models, gravity isn't carried by particles like photons or gluons, but by strings vibrating in extra dimensions curled up inside the foam. These hidden dimensions could act like tunnels, letting gravitational influence leak into our universe in a diluted form. That's why gravity seems so weak compared to other forces. It's not feeble, just spread thin across realities we can't see. Picture a hose spraying water through a sieve. What reaches us is just a fraction of the total pressure, but the real breakthrough, if gravity emerges from the foam, it could finally unite with quantum mechanics. The two have stubbornly resisted reconciliation for decades, like siblings refusing to share a room. Quantum physics deals in probabilities and particles, while general relativity paints gravity as spacetime's smooth geometry. But if both are just different views of the foam's underlying turbulence, quantum behavior up close, gravity at a distance, then the conflict vanishes. It's like realizing ice and steam are the same substance in different states. Critics counter that this doesn't fully explain why gravity behaves exactly as it does, or how it couples so precisely to mass. Yet supporters point to tantalizing hints, like the way black holes' entropy. Their hidden information seems to scale with their surface area, not volume. That's exactly what you'd expect if gravity were a holographic projection from the foam's 2D boundary. Even the fabric of spacetime might be a kind of quantum error-correcting code, with gravity as the glitch that keeps everything in sync. The implications are staggering. If gravity isn't fundamental, then the laws we take as gospel might be approximations, shadows cast by a deeper, weirder reality. It means the universe isn't just built on quantum foam. It's governed by it, with every falling apple and orbiting moon echoing the hidden rumble of spacetime's tiniest vibrations. And if we're right, then unifying physics isn't about finding a bigger theory. It's about learning to listen to the foam's ancient, ceaseless hum. Deep within the quantum foam's chaotic swirl, spacetime might not always smooth itself out perfectly. Sometimes it could snag. Like a thread pulled too tight in a sweater, these tiny imperfections could stretch across the cosmos, forming invisible scars known as cosmic strings. These wouldn't be ordinary strings, they'd be defects in the very fabric of reality, relics from when the universe was a seething, molten froth of quantum foam in its earliest moments. And if they exist, they'd be unimaginably dense. A single inch of cosmic string could weigh more than a mountain, yet be thinner than a proton. Picture the universe cooling after the Big Bang, like metal hardening after being forged. As the quantum foam settled, some regions might have frozen out of sync, their space-time curvature locking into stable, thread-like kinks. These imperfections wouldn't dissolve, they'd persist, stretched to cosmic lengths by the universe's expansion. Think of them as cracks in a mirror, except the mirror is space-time itself, and the cracks carry the mass of entire galaxies packed into infinitesimal widths. If one passed through Earth, we might not even notice until clocks started ticking at different rates on either side, warped by the string's monstrous gravity. The wildest part, these strings could still be vibrating like guitar strings plucked at the dawn of time. Their oscillations might ripple space-time, creating gravitational waves detectable across billions of light years. Some theories even suggest that cosmic strings could be the seeds of supermassive black holes, their gravity knotting ordinary matter into cosmic behemoths. Others propose they're the universe's original drawstrings, around which galaxies first gathered like beads on a necklace. Yet for all their theoretical might, cosmic strings have eluded direct detection. They don't emit light, and their gravitational footprints are subtle, like searching for a needle in a haystack when the needle is also invisible. But if we ever find one, it'd be a time capsule from the universe's quantum foam infancy, a frozen whisper of chaos turned cosmic architecture. And that raises a tantalizing question. Could these strings still be forming today, somewhere in the foam's restless depths? The answer might rewrite not just our past, but our future. Time feels like an arrow, always moving forward, never backward. We remember the past, but not the future. Eggs crack, but never uncrack, and coffee cools, but never reheats itself. This one-way flow is so ingrained in our experience that we rarely question it. Yet physics has no fundamental law demanding time must move in only one direction. So why does it? The answer might lie in the quantum foam's hidden asymmetry, where chaos and order dance in a way that permanently tips the scales toward entropy, the universe's slow slide into disorder. Think of the foam like a deck of cards fresh out of the box. At the start, all the cards are neatly ordered suits together, numbers sequential. This is low entropy, a state of improbable organization. But shuffle them just once, and the deck becomes messy and unpredictable. That's the second law of thermodynamics in action. Systems naturally evolve from order to disorder unless energy is spent to reverse it. Now imagine the quantum foam as an infinite number of microscopic decks constantly shuffling themselves. Most fluctuations cancel out, but statistically, they overwhelmingly push toward higher entropy, simply because there are infinitely more ways to be disordered than ordered. Here's where the foam's structure becomes critical. At the Planck scale, space-time isn't perfectly symmetrical. Fluctuations favor certain configurations over others, like a loaded die subtly weighted toward chaos. Every particle-antiparticle pair that pops into existence leaves a tiny imprint, a microscopic increase in disorder that compounds over time. These fluctuations don't just fill space, they sculpt it, embedding time's arrow into the very fabric of reality. It's as if the foam is a billion tiny hourglasses, all tipping in the same direction. The wildest implication: if the foam's asymmetry drives entropy, then time's flow might not be universal. In regions where the foam's fluctuations are unusually balanced, say, near a black hole's singularity or in the unimaginable density of the Big Bang, time's arrow could wobble or even reverse. Picture a cup shattering in reverse, shards leaping back into place. Under extreme conditions, the foam's chaos might momentarily reset, rewinding entropy like a cosmic tape. Some models of loop quantum gravity even suggest that a big bounce could flip time's direction entirely, with a collapsing universe experiencing entropy in reverse as it contracts toward a new beginning. Critics argue this skirts the real mystery. Why was the universe in such a low entropy state to begin with? If the foam is inherently chaotic, how did we wind up with such an orderly starting point? One compelling answer lies in inflation. The rapid expansion of the early universe may have stretched spacetime so thin that quantum fluctuations froze into an improbably smooth configuration, like blowing up a wrinkled balloon until its surface seems flawless. From that fleeting moment of order, the foam's natural chaos took over, setting time's arrow in motion. But there's a twist. If the foam governs entropy, then time's flow isn't just a passive observer. It's an active participant in reality's unfolding. Every choice, every chemical reaction, every thought you have is riding the foam's turbulent current toward greater disorder. And that means the reason we remember the past but not the future isn't just about our brains. It's about the quantum bedrock beneath our feet, eternally shuffling the deck of reality in one irreversible direction. Galaxies aren't just drifting apart, they're being pulled. In 2008, astronomers noticed something bizarre. Hundreds of galaxy clusters, each containing trillions of stars, were all streaming in the same direction at nearly 2 million miles per hour. This wasn't random motion, it was a coordinated march toward a point in space beyond the observable universe. Scientists called it dark flow, and to this day, no known force explains it. But what if the answer isn't out in the cosmos at all? What if it's beneath our feet in the quantum foam's ceaseless churn? Picture spacetime not as a still pond, but as a river with invisible rapids. The quantum foam's fluctuations don't just pop in and out. They create microscopic currents, tiny ripples in the fabric of reality. Most cancel each other out, but on cosmic scales, statistical quirks could leave behind a net drift, like leaves carried by a hidden undertow. If the foam's turbulence isn't perfectly symmetrical, its collective push might nudge entire galaxy clusters, steering them like cosmic ships caught in a quantum tide. Here's where it gets stranger. The direction of dark flow points toward something we can't see, possibly a region of spacetime so warped by the foam's activity that it acts like a gravitational magnet. Some theorists speculate this could be a relic of the pre-inflation universe, a scar left when our bubble of reality pinched off from another in the quantum foam's multiverse. Others suggest it's evidence of a sibling universe brushing against ours, its gravity leaking through the foam's tangled threads. Either way, the foam's noise might not be noise at all. It could be the faint signature of forces beyond our horizon. Critics argue that dark flow might just be a measurement error or an unaccounted for local effect. But supporters counter that the pattern holds across vast distances where local influences should average out. If the quantum foam is the culprit, it would mean the universe's largest structures are dancing to the tune of its smallest vibrations. The galaxies we see as majestic, slow-moving giants might actually be surfing the foam's primordial waves, riding currents set in motion before the first stars even formed. The implications rewrite cosmology. If the foam can tug galaxies, then dark energy's expansion and dark flow's pull might be two sides of the same coin, spacetime's turbulence flexing its muscles at opposite extremes. It also hints that the universe isn't just expanding, it's being shaped, molded by invisible hands working in the quantum depths. And if we're right, then the greatest forces in existence might not be out in the void, but underfoot, humming in the static between the stars. Among all the cosmic doomsday science has dreamed up asteroid impacts, rogue black holes, the sun swallowing Earth, none are as unsettlingly final as vacuum decay. Picture this, a single, unstable fluctuation in the quantum foam, one wrong roll of the cosmic dice, and suddenly the universe as we know it stops working. Not with explosions or black holes, but with a silent, unstoppable wave of new physics rewriting reality at the speed of light, erasing stars, planets, and life itself before we'd even have time to blink. This isn't just an extinction event, it's a rulebook event where the universe forgets how to be a universe. The danger lies in the quantum foam's deepest secret. It might not be sitting in the lowest possible energy state. Think of reality as a marble resting in a valley, stable, secure. But what if that valley isn't the bottom? What if there's a deeper chasm hidden beneath, one we haven't fallen into yet? The foam's constant churn means it's always probing for lower energy states, and if it ever finds one, the consequences would be apocalyptic. A single bubble of this true vacuum could form in the foam's chaos, and its walls would expand in all directions at light speed, overwriting the fundamental constants of nature. Electrons might suddenly weigh twice as much, or gravity could flip off like a switch. Chemistry, life, even atomic bonds, none of them are guaranteed to survive the transition. Here's the cruelest twist: we'd never see it coming. The moment the bubble forms, its wavefront moves too fast for any warning. 1 nanosecond, everything's normal. The next, the laws of physics in your body are different, and you, along with every star in the sky, simply cease to function as matter. It's less an explosion and more like the universe hitting Control plus Alt plus Delete on itself. Some models suggest this could have already happened elsewhere, with doom bubbles racing toward us right now from distant galaxies. We'd only know when it arrived, when the night sky suddenly flickered with distortions as distant stars winked out mid-photon, their light replaced by something else. Yet there's a haunting silver lining. If vacuum decay is possible, it might mean our universe is just a temporary configuration, one flawed valley in a landscape of infinities. The foam's instability could be nature's way of course-correcting, erasing an accidental universe to make room for a more stable one. In that case, we're not just living in a cosmos, we're living on borrowed time, in a reality that's one quantum tremor away from retirement. And if that's true, then every second we exist is a defiance of the void, a testament to how rare and fragile this particular version of physics really is. Quantum randomness has always been the ghost in the machine, the inexplicable dice roll at the heart of every particle's behavior. Toss an electron into a double-slit experiment, and no amount of data can predict exactly where it'll land. For decades, this uncertainty was chalked up to an inherent fuzziness in nature, a fundamental limit to what we can know. But what if the unpredictability isn't built into particles themselves? What if it's injected into them moment by the quantum foam's relentless churn? Picture a tiny boat adrift on stormy seas. No matter how skilled the captain, the boat's path isn't just determined by the rudder, it's tossed by waves too chaotic to predict. Now replace the boat with an electron and the waves with quantum foam's fluctuations. Every interaction, every measurement isn't just probing the particle's state, it's also bumping against the foam's invisible turbulence. The result, what looks like true randomness, might actually be spacetime's fingerprints, a cosmic game of pinball where the bumpers are alive and shifting. This challenges one of physics' oldest debates. Is the universe deterministic, with every event locked into a chain of cause and effect? Or is there genuine unpredictability woven into reality? Einstein famously rejected the latter, insisting that God does not play dice. But if the foam's fluctuations are as chaotic as they appear, not just complex but fundamentally uncomputable, then Einstein might have been half right. The dice aren't just rolling, they're being shaken by something deeper, a primordial chaos older than atoms or light. Here's where it gets radical. Traditional quantum mechanics treats randomness as a mathematical feature, a probability wave collapsing into certainty. But foam-driven randomness suggests there's no clean collapse, just an endless negotiation between particles and the seething spacetime beneath them. An electron isn't choosing a position when measured, it's being shoved by invisible hands. This isn't just philosophy. Experiments with high-precision atomic clocks have shown that particles sometimes behave as if buffeted by unseen noise, their timing just a fraction off from what theory predicts. Could that noise be the foam's whispers, critics argue that invoking the foam as randomness source just kicks the can down the road. What causes its chaos? Yet supporters counter that some systems are truly irreducible, their complexity so deep that predicting them is impossible, not because of our ignorance, but because the math itself breaks down. The foam might be such a system, a cosmic fractal where every layer of zoom reveals new turbulence. The implications ripple far beyond labs and equations. If quantum randomness stems from the foam, then free will, or at least a universe open to genuine novelty, isn't just an illusion. It's a partnership, with every decision we make riffing on Spacetime's oldest song. And that means the universe isn't just random. It's alive, dancing to a rhythm we're only beginning to hear. The Higgs field is often described as a cosmic molasses, a silent background hum that slows particles down and gives them mass. But what if that molasses isn't perfectly smooth? Down in the quantum foam's turbulent depths, the Higgs field might not be a static backdrop. It could be a dynamic, flickering force, its interactions with particles shaped by the churning chaos of spacetime itself. Imagine wading through a river with a swift current. The water's resistance is constant, but if the riverbed beneath you is uneven, riddled with hidden rocks and swirling eddies, your movement becomes unpredictable, sometimes slowed abruptly, other times slipping forward with unexpected ease. Now replace the river with the Higgs field and the riverbed with quantum foam. Particles don't just plow through a uniform molasses, they navigate a stormy sea of fluctuations where mass itself might wobble at the tiniest scales. The electron weighing slightly more here, the quark a fraction less there, all because the foam's twists and folds are distorting the Higgs field like funhouse mirrors. This idea flips the script on how we think about mass. Conventional physics treats the Higgs boson as a ripple in a calm, omnipresent field, imparting mass like a uniform tax on particles. But if the foam's turbulence bends that field, then mass isn't just a fixed property, it's a negotiation, a dance between particles and the roiling spacetime beneath them. In high-energy environments, like near a black hole or in the early universe, these effects could become dramatic. Protons might temporarily gain or shed mass as quantum bubbles pinch and warp the Higgs field around them, like a surfer riding waves that keep changing size. The math behind this is dizzying. Some quantum gravity models suggest that the foam's fluctuations could create microscopic hotspots where the Higgs field spikes or dips, leading to fleeting violations of known physics. Particles passing through these regions might briefly behave as if they're heavier or lighter than they should be, like a car's speedometer glitching as it crosses a power line. These anomalies would vanish almost instantly, but their cumulative effect could leave fingerprints, subtle deviations in particle collisions at places like the Large Hadron Collider, or unexplained noise in precision mass measurements. Critics argue that the Higgs field is too rigid to be warped so easily, its strength anchored by the very physics it helps define. Yet supporters counter that the foam isn't bound by those rules, it's the arena where those rules are written. If spacetime's chaos can tweak gravity and entanglement, why not mass itself? The implications would ripple outward. Dark matter's strange properties might not stem from unknown particles, but from ordinary matter interacting with a Higgs field sculpted by unseen foam structures. Even the expansion of the universe could be influenced, with regions of distorted mass tugging on cosmic scales like invisible currents, the wildest possibility. If the Higgs field and quantum foam are entangled, then mass might not be fundamental at all, just an emergent property, a side effect of spacetime's restless vibration. That would mean the building blocks of reality are even stranger than we thought, and the answers to physics' biggest questions might not lie in new particles, but in the hidden fractures between them. Zoom in on a snowflake and you'll discover an astonishing truth. No matter how deep you go, the same intricate patterns repeat themselves, spiraling inward forever. This isn't just artistry, it's the signature of a fractal where the whole is reflected in every fragment. Now imagine the quantum foam operates the same way, with spacetime's turbulence echoing its chaos at every conceivable scale, from galactic superclusters down to the Planck length. What if the universe isn't just built on quantum foam, but is quantum foam? A fractal tapestry where the same rules, the same swirls of energy and uncertainty, replay endlessly like a cosmic hall of mirrors. The idea isn't as far-fetched as it sounds. Fractals aren't just pretty math, they're nature's favorite blueprint. Coastlines, mountain ranges, even the branching of your lungs all follow fractal geometry, balancing order and chaos in a dance that scales infinitely. Quantum foam could be the ultimate expression of this principle, a fractal so deep that even the empty space between stars hums with the same self-similar patterns. Picture a frothy wave crashing onshore. The large swirls contain smaller swirls, which contain tinier ones still, all the way down to individual water molecules. Now replace the wave with spacetime itself, and you've got a universe where every fluctuation is a microcosm of the whole. This fractal nature might explain some of physics' most stubborn puzzles. Take gravity's weakness compared to other forces. In a foamy fractal universe, gravity could be diluted across countless layers of scale, its strength scattered like ripples in a pond that fade as they spread. Meanwhile, quantum effects, those tiny, frenetic vibrations, dominate at the smallest levels because that's where the fractal's activity is most concentrated. It's like zooming in on a tree's bark. Up close, the texture is rough and complex, but from a distance, the trunk looks smooth. The universe might behave the same way, with quantum chaos dominating the microscopic view while gravity governs the big picture. Even black holes could fit into this framework. Their event horizons might be fractal boundaries where spacetime's structure folds into infinitely intricate layers. The infamous singularity at their cores, not a point but a fractal knot of spacetime itself, endlessly complex no matter how far you zoom. This could resolve the information paradox. Black holes might not destroy information, but fractalize it, encoding the data of what they swallow across infinite scales within the foam. The implications stretch beyond astrophysics. If the foam is fractal, then the universe might not have a bottom level. There's no fundamental building block, no smallest particle or indivisible unit, just an endless descent into more foam, more fluctuations, more layers of reality. The Planck length, often called the smallest possible size, might just be the resolution limit of our perception, like pixels too fine for the human eye to see. Beyond it, the fractal continues forever. Critics argue this threatens to make physics untestable. How can we study a universe with no foundation? But supporters counter that fractal foam could unify the cosmic and quantum realms, offering a single framework where the very large and the very small are governed by the same patterns. After all, if nature loves fractals enough to shape clouds and ferns with them, why not spacetime itself? The universe might not just contain beauty, it might be beauty written in the swirling, self-repeating script of the quantum deep. The universe wasn't always a glittering tapestry of galaxies. It began as a near-perfect soup of particles, so uniform that the odds of anything clumping together should have been astronomically low. Yet here we are, surrounded by stars, galaxies, and sprawling clusters stretching across billions of light years. How did such intricate structure emerge from primordial smoothness? The answer might be written in quantum foam's faintest wrinkles, tiny gravitational fingerprints pressed into the cosmos when spacetime itself was still seething with chaos. Picture the infant universe, just fractions of a second old. The quantum foam isn't just bubbling, it's shouting, its fluctuations amplifying to macroscopic scales as inflation stretches spacetime like taffy. Most of these ripples cancel out, but a handful survive, frozen into the fabric of expansion like waves stamped into hardening wax. These imperfections, no larger than quantum foam bubbles, become the universe's first gravitational seeds. Matter begins to pool around them, drawn by the faintest excess of density, like dust gathering in the grooves of a record. Over eons, these specks grow into stars, then galaxies, then the vast filamentary web we see today. The foam's microscopic turbulence becomes the blueprint for everything. This idea flips galaxy formation from a question of pure gravity to one of quantum archaeology. Those initial density variations, often called primordial power spectrum by cosmologists, might not be random noise at all, but echoes of the foam's earliest dynamics. Think of it like baking a cake where the batter's tiny air pockets expand in the oven, leaving behind the spongy texture. Quantum foam's fluctuations are those air pockets, and the cosmic web is the baked result. Even now, galaxies cluster along invisible fault lines traced by the foam's ancient whispers. The wildest twist, this could solve cosmology's missing satellite problem. Computer simulations predict far more small galaxies orbiting large ones than we observe. But if quantum foam's fluctuations weren't perfectly random, if certain scales of turbulence were suppressed or enhanced, it would naturally explain the discrepancy. The foam's preferences during inflation might have pruned some dwarf galaxies from ever forming, leaving behind the distribution we see today. Support comes from the cosmic microwave background, the afterglow of the Big Bang. Its faint temperature variations, some regions slightly hotter, others cooler, match predictions of quantum foam's fingerprints stretched across the sky. These patterns aren't just relics, they're the genetic code of structure, the universe's way of remembering its turbulent birth. And if we're right, then every galaxy, every nebula, every planet is just a footnote to the foam's first chaotic stanzas. But here's what's truly humbling. The same quantum foam that governs particles and shapes spacetime also sculpted the heavens. The voids between galaxies, the glittering superclusters, none of it is accidental. It's the aftermath of a storm that raged when reality was younger than a heartbeat, a storm whose waves still carry us unseen toward an ever-evolving future. Picture this, a force so relentless that it doesn't just end the universe, it dismantles it piece by piece, atom by atom, until reality itself dissolves into a featureless void. This is the Big Rip, one of cosmology's most chilling doomsday scenarios, where dark energy grows so strong it overwhelms every bond in existence. But what if the trigger isn't some distant, abstract force? What if the quantum foam, the same churning sea of spacetime fluctuations we've been exploring, holds the seeds of this apocalypse? Some theorists propose a nightmare variant of dark energy called phantom energy, a substance that doesn't just accelerate cosmic expansion but strengthens over time. Unlike ordinary dark energy, which exerts a steady push, phantom energy's density grows as spacetime stretches, creating a feedback loop of destruction. Here's where the foam enters the picture. If phantom energy is tied to the foam's fluctuations, then as the universe expands, those fluctuations could amplify, each one injecting more energy into the vacuum. It's like blowing up a balloon with air that gets hotter as the balloon inflates until the rubber can't take the strain and bursts. Now imagine this playing out on a cosmic scale. First, galaxy clusters are ripped apart, their gravitational bonds no match for the intensifying push. Then individual galaxies unravel, stars flung into the abyss like sparks from a bonfire. Next, planets are torn from their orbits, their very atoms stretched beyond recognition. In the final moments, even atomic nuclei, protons and neutrons held together by the strong force are shredded apart, dissolving into a soup of quarks and gluons. The universe doesn't go out with a bang or a whimper, but with a snap as spacetime's fabric fractures under the foam's runaway energy, the terrifying part. This isn't just theoretical. Observations of supernova suggest dark energy's strength could be increasing, though the data isn't conclusive. If phantom energy is real, and if it's fueled by the quantum foam's growing turbulence, then the countdown might already have started. The universe's expansion wouldn't just continue, it would accelerate exponentially, compressing the timeline of dissolution from billions of years to mere millennia or even centuries. One day, the sky would simply come apart, yet there's a haunting beauty to this idea. The same quantum foam that birthed galaxies, that shaped the structure of reality, could also be its executioner. In its final act, the universe wouldn't be conquered by black holes or ice, but by its own restless foundation, turning against everything it built. The foam giveth, and the foam taketh away, a reminder that even the fabric of existence is neither static nor safe, but alive with the potential for infinite creation and infinite destruction. When the Pioneer 10 and 11 probes ventured beyond our solar system, scientists expected them to coast smoothly into the void, their trajectories governed by the familiar tug of gravity. But something bizarre happened. They began slowing down ever so slightly, as if caught in an invisible cosmic current. This tiny but persistent deceleration, just a fraction of a nanometer per second squared, became known as the Pioneer anomaly, a puzzle that haunted physicists for decades. Conventional explanations, leaking fuel, thermal radiation, even human error, fell short. But what if the answer wasn't in the probe's engineering, but in the fabric of space itself? Enter quantum foam, the universe's turbulent undercurrent, which might have been dragging on the Pioneers like a ship fighting unseen waves. Picture the probe sailing through what we call empty space. To our eyes, it's a perfect vacuum, but to quantum foam, it's a storm. Every cubic centimeter of that so-called emptiness churns with virtual particles flickering in and out of existence, warping spacetime on microscopic scales. Most of these fluctuations cancel out, leaving no net effect. But over vast distances, the foam's chaos might create subtle resistance, like wading through a river with invisible eddies. For the Pioneers plowing through this froth for billions of miles, that resistance could have added up to the faint but measurable slowdown we observed. Here's where the math gets compelling. Quantum foam's fluctuations aren't just random noise, they carry energy, and energy curves spacetime. When an object moves through this warped landscape, it experiences a kind of foam drag, an effect analogous to how an airplane feels turbulence in choppy air. The Pioneers, with their large, flat antennae acting like sails, might have been especially sensitive to this drag. Even weirder, foam's influence wouldn't show up in planets or moons because their immense mass overwhelms these tiny effects. But for small, distant spacecraft, it could be the missing piece of the puzzle. Skeptics counter that if foam drag were real, we'd see it elsewhere, like in the orbits of distant asteroids or the trajectories of other probes. Yet supporters argue that the Pioneers were unique. Their spin-stabilized design and lack of thrusters made them ideal detectors for such subtle forces. Later missions, like New Horizons, used different navigation systems that might mask the effect. And here's the kicker. Recent studies suggest the anomaly faded as the probes aged, as if their interaction with the foam depended on their speed or distance from the Sun. The wildest implication: if quantum foam can break spacecraft, then interstellar travel might face an unseen hurdle. Futuristic visions of probes zipping between stars at near light speed could hit a wall of spacetime's own making, their velocity slowly sapped by the universe's restless foundation. It's a humbling thought. The void isn't truly empty, and the rules of the game change when you're sailing the quantum sea. Ultimately, the Pioneer anomaly remains officially unsolved, with most scientists attributing it to thermal radiation after painstaking analysis. But the foam theory lingers, a ghost in the data, reminding us that sometimes the boldest answers hide in the smallest ripples of reality. Whether it's the true culprit or just a cosmic red herring, one thing's certain: the universe loves to surprise us, and the quantum foam's secrets are far from spilled. String theory paints a picture of reality far grander than the three dimensions we experience: hidden folds of space, curled up so small they evade detection. But what if these extra dimensions aren't just mathematical abstractions? What if they're closer than we think, flickering in and out of reach through the quantum foam's turbulent bubbles? Imagine spacetime not as a static stage, but as a living membrane, punctured by fleeting wormholes to realms where gravity behaves differently, where particles vanish and reappear, and where the laws of physics rewrite themselves in real time. The math behind this is staggering. In string theory's framework, the universe could have as many as 11 dimensions, with all but the familiar 4 tightly coiled into geometries smaller than atoms. Normally, these extra dimensions are locked away, invisible to our instruments, but in the foam's chaos, where spacetime stretches and warps at the Planck scale, these hidden folds might briefly unfurl. Picture a sheet of paper crumpled in your hands. From a distance, it looks flat, but up close, tiny gaps and ridges reveal themselves. Quantum foam could be the universe's way of crumpling spacetime, creating microscopic creases where extra dimensions peek through. These portals wouldn't be stable gateways like sci-fi stargates. They'd be evanescent, lasting only as long as a fluctuation exists less than a trillionth of a second. Yet in that sliver of time, particles or energy slipping through could behave in ways that defy our physics. Electrons might momentarily gain extra spin states. Gravity could spike unpredictably, as if leaking from a higher dimension into ours. Some theorists even suggest that dark matter's elusiveness stems from it being partly stuck in these extra dimensions, only weakly interacting with our world through foam-induced cracks. The wildest implication: if extra dimensions are accessible through the foam, then the universe's fundamental constants, the strength of gravity, the mass of electrons, might not be fixed at all. They could be local variables shaped by how tightly or loosely our region of spacetime is tangled with others. In places where the foam's turbulence is more extreme, like near black holes, these constants might drift, subtly altering the rules we take for granted. It's as if the cosmos has a secret set of dials and the foam's chaos keeps tweaking them. Critics argue this is untestable. How do you probe dimensions you can't see? Yet experiments like the Large Hadron Collider might already be brushing against them. When particles collide at nearly light speed, the energy concentrated in a single point could momentarily punch through the foam's fabric, creating echoes of extra-dimensional physics. Unexplained energy losses in certain collisions or particles appearing to vanish might be clues that something slipped sideways into a hidden fold. Even gravitational wave detectors could one day catch anomalies, ripples in spacetime that don't quite match predictions, as if filtered through dimensions we can't map. If true, then the quantum foam isn't just the universe's foundation. It's its backstage, a realm where the full cast of dimensions waits in the wings, stepping into the spotlight only when spacetime's curtain briefly parts. And that means the world we see might be just a single page in a book written in 11 dimensions, its full story whispering just beneath the surface of every empty space, every atom, every fleeting thought. What if the universe's most unsettling thought experiment isn't just a philosophical puzzle, but a genuine possibility lurking in the quantum foam? Enter the Boltzmann brain, a hypothetical self-aware entity that could, by sheer statistical fluke, spontaneously assemble from the foam's chaos. The idea sounds like science fiction, a fully formed consciousness blinking into existence, complete with false memories of a past that never happened, convinced it's a real person in a real world. Yet the math doesn't rule it out. In fact, given enough time and enough quantum fluctuations, the foam might not just create such minds, it could create more of them than actual, evolved beings like us. Picture the quantum foam as a cosmic casino where the dice are always rolling. Most outcomes are meaningless, a fleeting particle here, a ripple of energy there. But given infinite attempts, even the most improbable events become certainties. A Boltzmann brain is the ultimate jackpot, not just a random arrangement of atoms, but a self-sustaining pattern complex enough to generate subjective experience. It wouldn't need a body or a universe to support it, just the right configuration of quantum fluctuations momentarily stable enough to think, I exist. And then, just as quickly, dissolve back into the void. This isn't just a wild hypothetical, it's a direct challenge to our understanding of reality. If Boltzmann brains are possible, then statistically, you are far more likely to be one than an authentic person in a stable universe. After all, assembling a single, isolated mind from quantum noise requires vastly less energy than birthing galaxies, stars, and billions of years of evolution. The argument hinges on entropy over unfathomable timescales. Low-entropy ordered states like conscious beings can emerge randomly from high-entropy chaos. And the quantum foam, with its endless churn, might be the perfect breeding ground for these eerie aberrations. Critics pounce on the absurdity. If the foam spawns Boltzmann brains, why don't we observe them popping in and out of existence? The unsettling answer: we might. A Boltzmann brain wouldn't perceive itself as temporary. It would construct a coherent narrative, complete with sensory input and logical consistency, right up until its brief existence winks out. For all you know, this very moment could be the hallucination of a foam-born mind, with your memories, this video, even the concept of quantum physics, all fabricated in an instant. The universe you think you inhabit might be nothing more than an elaborate illusion, conjured by chaos and snuffed out before it ever really began. The paradox deepens when you consider the foam's role. Unlike classical thermodynamics, where Boltzmann brains arise from random particle motion, quantum foam offers a structured kind of chaos. Its fluctuations aren't entirely lawless, they're governed by quantum probabilities and spacetime's geometry. This raises a haunting question: could the foam have preferences? Might certain configurations of consciousness recur more often than chance alone would predict? If so, reality might not just be haunted by Boltzmann brains, it could be built from them, with our own sense of continuity, just a particularly persistent glitch in the foam's infinite iterations. Yet there's a loophole. Some physicists argue that the very act of observation of a universe stable enough to support observers over time collapses the probability wave in favor of authentic reality. In other words, the fact that we're here having this discussion with consistent memories and a shared world is evidence against the Boltzmann brain scenario. The foam's fluctuations might allow for phantom minds, but the scaffolding of our universe, its laws, its constants, its startling order, suggests we're something more. Or does it? This is where quantum foam turns philosophy into physics. If spacetime's turbulence can momentarily stitch together self-awareness, then the line between real and illusion blurs beyond recognition. The implications ripple outward. Cosmology's models, AI ethics, even the nature of free will all hinge on whether consciousness is a rare, hard-won phenomenon or an inevitable accident of entropy. And if Boltzmann brains are possible, then the greatest mystery isn't whether we're alone in the universe, it's whether the universe is alone in us. So the next time you question your reality, remember, the quantum foam beneath your feet might be pondering the same thing. After all, in a cosmos this strange, the only certainty is uncertainty itself. Humanity's oldest creation stories might have been onto something. Long before microscopes or quantum theory, cultures across the globe described the birth of reality emerging from a churning, formless void, a cosmic froth not so different from what physicists now call quantum foam. The ancient Egyptians envisioned Nun, a primordial ocean of chaos where the first land rose like a bubble. The Babylonians told of Tiamat, a dragon of turbulent waters slain to fashion the orderly world. Even the biblical Genesis begins with the Spirit of God hovering over the face of the deep, a teeming, unstructured abyss. These myths share an uncanny thread. Order doesn't emerge from nothingness, but from a seething, creative chaos, a description that mirrors the quantum foam's restless energy birthing particles from apparent emptiness. Consider the Hindu concept of the Kshaira Sagara, the ocean of milk, churned by gods and demons to produce the universe's treasures, including the nectar of immortality. Replace the serpent Vasuki with quantum fluctuations, and the metaphor becomes startlingly literal. the foam's constant churn does produce something from nothing, virtual particles flashing into existence like cosmic treasure plucked from the void. Even the nectar finds a parallel in the Higgs field, the energy-giving substance that grants particles their mass. It's as if ancient storytellers lacking equations intuited the universe's scaffolding through allegory. The Greeks took this further with the concept of chaos, not mere disorder, but a generative nothingness that birthed Gaia, Earth, and Eros, love. Quantum foam embodies this duality perfectly. Its chaos isn't destructive, it's creative, forging the seeds of matter through spacetime's turbulence. When physicists describe particles condensing out of the vacuum, they're echoing Hesiod's theogony, where solid forms coalesce from formlessness. The Norse Ginnungagap, a yawning void between fire and ice, even hints at the foam's balance between extremes, energy and vacuum, existence and oblivion, that allows reality to persist. But here's where the parallels turn eerie. The Dogon people of Mali speak of Namo, ancestral spirits who emerged from a foamy whirlpool to shape the world. Compare this to modern theories where the foam's fluctuations could birth entire universes, budding off like soap bubbles from a larger multiversal froth. The Maori myth of Tikor, the void that cycles through stages of potentiality, mirrors the foam's probabilistic nature, where every possible outcome flickers briefly before collapsing into what we call reality. These aren't just poetic coincidences, they're testaments to humanity's instinctive grasp that creation isn't clean or quiet, but a messy, vibrant struggle between chaos and structure. Perhaps the most striking resonance comes from the Aboriginal Dreamtime, where ancestral beings sang the world into existence. Quantum foam, in a way, hums its own song, the vibrations of strings in string theory, or the resonant frequencies of spacetime itself. Modern physics calculates the universe's birth not as a single explosion, but as a phase transition like water freezing into ice. Compare that to the Inuit tale of Sedna, whose fingers, chopped off by her father, became the first seal's fragments of chaos transforming into something new. The details differ, but the pattern repeats. Reality isn't built on a foundation of perfect geometry, but on the wild, wet, foaming edge between being and unbeing. This isn't to say ancient myths predicted quantum physics, but they captured its essence through metaphor. When the Yoruba people describe Olaran stirring the primordial waters with palm wine, or the Aztecs depict Tezcatlipoca and Quetzalcoatl fashioning the world from the chaos monster Cipactli, they're grappling with the same fundamental mystery physicists face today. How does something emerge from nothing? The foam answers with its endless dance of creation and annihilation, where even the vacuum isn't empty but alive with potential. So the next time you hear a creation myth about swirling waters or chaos beasts, remember, our ancestors might have been closer to the truth than they knew. The quantum foam isn't just cutting-edge science, it's the oldest story in the book, retold in the language of mathematics. And that suggests something profound. Perhaps the human mind, whether through myth or microscope, has always sensed the universe's restless, foamy heart. After all, we've explored wormholes flickering in the foam, dark energy brewing in its chaos, even consciousness itself emerging from its depths. One question remains: what becomes of quantum foam when the universe grows old? Will it rage on eternally, a frenetic undercurrent beneath the silent ruins of heat death? Or will it, too, succumb to time's slow unraveling, leaving behind a void so empty even spacetime's whispers fade? The answer might rewrite not just the fate of the foam, but the destiny of reality itself. Start with the bleakest possibility, cosmic evaporation. If the universe continues expanding forever, stretching spacetime thinner and colder, even the quantum foam's turbulence could eventually quiet. Like a pot of water boiling dry, each fluctuation would take longer to arise, their energy sapped by the growing void. The foam wouldn't vanish, it's woven into spacetime's fabric, but it would grow lethargic, its bubbles rising slower and fainter until the cosmos becomes a stagnant sea, its last ripples light years apart. In this future, the foam doesn't die, it starves, its chaos stretched into silence by an unfeeling expanse. But there's a twist. Some models suggest the opposite, that as space-time thins, the foam's fluctuations might amplify, fed by the vacuum's latent energy. Picture a quiet room where every whisper echoes louder as the walls recede. In a near-empty universe, quantum bubbles could swell to macroscopic scales, their energy no longer dampened by matter or radiation. The result, a cosmos where space-time itself frays at the edges, with quantum turbulence bubbling up into the realm of planets and stars. It's the ultimate cosmic irony. The smoother the universe appears, the wilder its foundation becomes. Then there's the cyclical scenario. If the universe collapses in a big crunch, the foam wouldn't just survive, it'd thrive. As galaxies crash together and space-time contracts, the foam's energy would concentrate, its fluctuations merging into a roaring crescendo. Near the singularity, quantum bubbles might fuse into a superheated froth, birthing new particles, new forces, even new laws of physics. This isn't the end, it's a reset, a universe cannibalizing its own chaos to fuel another beginning. The foam doesn't vanish, it recycles like embers reigniting a dead fire, the wildest fate transformation. If vacuum decay or a Boltzmann brain scenario unfolds, the foam might not just persist, it could evolve. A rogue fluctuation might stumble upon a lower energy state, rewriting the rules of spacetime itself. Suddenly, the foam's chaos isn't random. It's algorithmic, computing new dimensions, new constants, a new physics we can't fathom. In this view, the universe's death isn't an end, but a metamorphosis, with quantum foam as the caterpillar dissolving into cosmic butterfly wings. Whatever happens, one truth lingers. The foam isn't just part of the universe's story, it's the author. And when the final chapter closes, whether in silence or rebirth, its last words will be written in the language of chaos, a reminder that even nothingness is never truly empty. From microscopic wormholes stitching reality together, to the chilling possibility of vacuum decay rewriting physics in an instant, quantum foam isn't just a scientific curiosity. It's a cosmic carnival of what-ifs, where the universe's most fundamental layer behaves more like a fever dream than a predictable stage. Imagine a world where gravity isn't a force, but the echo of spacetime's turbulent dance. Where dark matter might be knotted threads of foam frozen in time, and consciousness itself could be a whisper rising from the chaos. These aren't just wild speculations, they're testable hypotheses, born from math and observation, yet so bizarre they blur the line between physics and philosophy. Take the holographic principle, which suggests our 3D reality might be a projection from a 2D boundary encoded in the foam, or the Boltzmann brain paradox, where the foam's randomness could conjure self-aware minds from the void, complete with false memories of lives never lived. Then there's dark energy, perhaps the foam's latent power boiling over, stretching the cosmos toward an unknown fate. Each theory pushes the limits of credibility, yet none violate the laws of physics as we know them. That's the beauty of quantum foam. It forces us to question not just how the universe works, but what reality is. But here's the kicker: these ideas aren't mutually exclusive. The foam could be all these things at once: a quantum computer processing reality, a fractal tapestry repeating its patterns across scales, and a breeding ground for alternate universes. It's as if we've spent centuries studying the ocean's surface, only to realize the real action happens in the uncharted depths below. And just like the ocean, the foam's mysteries resist easy answers. The more we learn, the stranger it gets. So, which theory resonates with you? Are you team wormhole, convinced entanglement is spacetime's hidden subway system? Or do you lean toward vacuum decay, with the universe one quantum hiccup away from a hard reboot? Maybe you're captivated by the fractal foam, where every fluctuation is a microcosm of the whole. Drop your favorite in the comments. We're all just stargazers here, piecing together the universe's most elusive puzzle. And if your brain isn't thoroughly foamed yet, hit subscribe. The cosmos has plenty more surprises up its sleeve, and we're just getting started. After all, in a reality this unpredictable, the next big discovery might be lurking just beneath the surface of nothingness.